Today we are walking through the paper titled LongCat-Next Lexicalizing Modalities as Discrete Tokens.
Give me the bit texture first.
This paper asks whether text, images, and audio can all be modeled as one next-tone stream, instead of bolting vision and audio onto a language model as side modules. LongCat-Next turns them into discrete tokens so one autoregressive model can read, reason, and generate across modalities.
What gap in earlier multimodal systems makes that hard?
The paper says earlier systems are still language-centric. They often attach continuous visual or audio features to a text model, which fragments the architecture and makes it hard to get strong understanding and strong generation at the same time.
So what is the paper's main move to get past that?
The answer is DNA, short for Discrete Native Autoaggressions. In the LongCat-Next architecture, parent tokenizer rests turn images and audio into discrete tokens, and the backbone processes text, vision, and audio under one autoregressive objective with minimal modality-specific machinery.
In that architecture, which part should I focus on first?
Focus on the fact that the tokenizer is not a sided actor. It is the interface that lexicalizes each modality into the same kind of object the language model already knows how to model, so the system can use one training recipe instead of stitching together separate pipelines.
Why is vision the hardest piece of that plan?
Because language tokenization is close to lossless for next-tone prediction, but images are dense and continuous. The paper argues discrete vision hit a ceiling because older roots either preserved pixels but not concepts, preserved concepts but not reconstruction, or kept up pixels in a wasteful form.
The paper keeps using the term semantic completeness. What does that mean here?
Semantic completeness means a discrete image code should support almost the same answer as the original image for a downstream question. That is the point of this condition on the board. If you ask the task through the tokens instead of the raw image, the model should reach nearly the same posterior answer.
And what practical requirements fall out of that definition?
The paper gives two. Discriminative invariance means the tokens must keep the semantic clues needed for recognition and reasoning. Generative sufficiency means they must also preserve enough structure to reconstruct the image, so understanding quality and generation quality are both protected.
How does DNAVIT actually try to satisfy those two requirements?
DNAVIT starts from a semantic aligned encoder, then uses residual vector quantization to build hierarchical visual tokens. That gives LongCat-Next a tokenizer that can both tokenize and detokenize at arbitrary resolution. And the paper says it can compress images by up to 28 times while keeping the semantics usable.
Why does the hierarchy matter instead of using one flat codebook?
Because the model quantizes the residual of the residual across levels. Coarser levels capture the global semantics first. Later levels recover the details that would otherwise be lost. And the paired detokenizer maps those tokens back into images at flexible resolutions.
Do they show evidence that the visual tokens still keep a coverable structure?
Yes. The reconstruction study argues that modern encoders already preserve a latent path for low-level signal through residual connections. That is why even a semantically trained frozen encoder can still support reconstruction. And it explains how the discrete interface can serve both reasoning and generation.
How do they extend the same idea to audio?
The audio tokenizer follows the same discrete native logic. Audio goes through a whisper encoder, gets downsampled, and then an 8-layer residual vector quantizer turns it into discrete tokens. A paired decoder and refiner reconstruct the waveform, while the language model sees audio as tokens rather than as an external continuous feature block.
What is new in the speech generation part, not just the tokenizer?
They train text-guided audio with stochastic delays between text and audio segments. That lets serial and parallel generation live inside one framework instead of being two separate systems, which matters if the same backbone is supposed to chat, iterate, and respond in real time.
Does that faster parallel mode hold up on quality?
The ablation says yes, mostly. On llama questions, parallel audio generation scores 79.33 versus 81.67 for serial generation. And on reasoning QA it scores 74.95 versus 80.30. So there is some loss.
Where do the strongest end-to-end results show up first?
On visual understanding, the model posts 88.0 on chart QA and 60.1 on chart arXiv, and it reaches 89.9 on chart arXiv, where the paper says it beats the other baselines on trails only Gemini to 0.5 flashlight. The message is that discrete visual modeling no longer has to accept a big understanding penalty.
What about image generation? A unified model usually gives something up there.
That is where the paper tries to show the trade-off is getting smaller. Against specialized text-to-image models, LongCat-Next scores 80 for 0.4 for on-gen evil and 93.15 on LongText-EN. That beats Gemini to 0.5 flash image on those two columns. So the result is not that specialization disappears.
So what is the clearest claim the paper earns by the end?
LongCat-Next argues that native multimodal GUI should look more like language modeling than like a bundle of attached encoders. By lexicalizing vision and audio into discrete tokens, the paper shows one model can see, generate images, and speak under one autogessive recipe, while narrowing the old gap between understanding and generation.
And what is the main limitation I should keep in mind?
The authors are explicit that this is an early industrial scale attempt, not a finished endpoint. Some studies use reduced settings because of compute cost, and they frame the work as a first step towards scaling native multimodal GUI further. But the core evidence is already concrete. The discrete interface is strong enough to support both multimodal understanding and multimodal generation.
So the core bet is that once the tokenizer becomes native, the rest of the multimodal system can stay much simpler.
Exactly. The paper's real contribution is turning modalities into a shared discrete language that one autogessive model can use end to end. That wraps up this paper walkthrough.